So as an introduction to deep learning, I will take you through the history, the philosophical history that leads us to this day, and you will see that this history is relevant both for your research and for this field in general. So unlike this ghostly ability to find commonalities between among objects, one thing that is not so weird is doing rational operations. For example, matrix multiplication. This slide also wants to make sure that everyone knows how to multiply matrices, because this is the basic building block of deep learning. So we are all on the same page. Here is, for example, one matrix that is called W. We'll call it weights. It has some values, an input vector X, and we need to calculate the multiplication of W times X. We call the output Y. Okay. How do we do that? Unlike when we needed to find the common thing shared among all of us, here you have a simple procedure. Simple, it is a relative term, but you have a certain procedure that you can do. You take the rows of the matrix, multiply by each element of this vector X, and you get the answer 0, 6. So you can do even more complicated matrix multiplication by taking, instead of an input vector X, you take a matrix that large X that includes several input vectors. Here you have the first one, and you see the same thing as this one, and other input vectors, and the multiplication of W times X will be all of the answers. The same thing you get in the first column, the answer for this input vector, and in the second column, the result for multiplying this input vector. This is the basic building block of deep learning. Okay, and as you've seen, this is a very rational thing to do. There is no argument about how to do it. There are no several true answers. There is only one true answer. So this type of operations motivated Descartes to try to find things, knowledge in a way which is as certain and clear as mathematics. Okay, so quote him, I perceived it to be possible to arrive at knowledge highly useful in life, and instead of the speculative philosophy usually taught in the schools, to discover a practical by means of which knowing the force and action of fire, water, of nature, the stars, the heavens, and all other bodies that surround us, as distinctly as we know the various crafts of our artisans. So he started this movement of trying to understand things, gaining knowledge. It goes before him, but he is our representative for that, for gaining knowledge through rational thought. The ideal that he set is to achieve certain, clear, and distinct knowledge, like in mathematics, and this philosophical view is called rationalism, gaining knowledge through reason and deductive logic. You all know what the deductive logic is, just want to make sure. Okay, if you are not certain about it, we'll see that mathematically formed. Okay, so inspired by Descartes, Newton came, found things that can be explained distinct and clear ways, in distinct clear ways, like gravity. You can write equations that are certain, that are mathematical, and describe nature using this rationalistic kind of explanation. This line of philosophical thought goes to our day, to science, to modern science. For example, this is a famous paper from ELSC people. One of them is Sokolinsky, and the other Van Rizwick, which died recently, and there is a conference dedicated to him towards the end of the year. They proposed a balanced state model of how neurons in the brain are balancing each other. Inhibitory neurons are inhibiting the excitatory neurons. Those that are not from neuroscience, it doesn't really matter, but they made a mathematical model that described some properties that are presumably a model of the brain. And the certainties are achieved usually in science, in rationalistic kind of science, by a reduction of the problem that we try to solve to some basic building blocks, to basic components, which we can then describe with deductive logic how they are developed in time. And another way to do it is by studying the statistics over a large number of things. If we're looking at the statistics, then you can do deductive logic on those statistics. Okay, this is the mathematical model. As a kind of a parallel direction that was within this rationalistic kind of avenue is trying to build rational machines. Those are our computers. Turing is the one that is responsible for that, and the first one to do it, building Turing machines. They try to model our rational kind of thought. So you have states, and you have a very clear logic in how these states evolve. If it is 0, then erase this memory slot. If it is then write 1, move right. You have a state machine that operates. These Turing machines are made. Computers are made of discrete Boolean logic components. Everything is very clear. And I just want to mention that from a rationalist perspective, building these Turing machines was artificial intelligence. They thought that intelligence, that human thought is rational, that it is made of this logic kind of deductions, and they tried to model it with machines, and we got Turing machines as a response. So I want to ask you, what are the limits that you can think of this deductive logic?
Creativity.
So you're confined in some way.
You have specific limits that can act within them, but to generate something completely creative like humans, it's still a grand challenge.
Mm-hmm.
Yeah. It can also be difficult when you don't have a lot of evidence. Psychology, they find like people use all kinds of heuristics and things that aren't necessarily rational when they use for an answer.
Yeah, so humans are not necessarily rational, and if you try to model them as such, you get problems. Okay. Yeah. Yeah. Who told us what are the axioms for this deductive logic? Yeah. Okay. All of these are the 3 points that I wanted to make, but I want to demonstrate it. So, for example, in neuroscience, in theoretical neuroscience, many times neurons are represented as a single number, and the connection between neurons is also a single weight. Those weight matrices that we saw earlier, and in the real world, neurons are way more complicated, and they are related with several synapses, and you don't really know whether you need to count the number of synapses to determine what the weight corresponds to. So the world is more complicated than this sometimes mathematical models, which can be important in some cases when this complexity is important for something that you want to know about. In art, many painters, and specifically Rene Magritte, tried to demonstrate, tried to tell us that to look at these limits of deductive logic. For example, what do you see here? What is this? Is this a horse? It is clearly not a horse because there are blank signatures here. So it is not a horse, but why do we think that this is a horse? And even if it was full, would we think that this is a horse? It is not a horse, it is a painting of a horse. And you extend this logic to your everyday life. So perhaps when you perceive something as a horse, or something that you see as a clear thing, a box, perhaps it is something, it is not exactly what you are perceiving. You're not doing it rationally. There is no rational explanation for why this is a horse. Or perhaps there is, but we'll see what it may be. Another example is Day of and Night by Escher. And by the way, this explanation is very similar to what is written in Gödel Escher-Bach book, if you are interested in expanding on this kind of discussion. The thing is, we try to say that this is a black bird and this is a white bird. And Escher tried to look at the intersection between the two. When, what is this? Is this a white bird? He tried to show us that, to explore these gaps between our clear boxes. So they had this attempt to tell us that rational logic deduction is perhaps not the way that humans are operating. We also see it technologically. So ImageNet is an image classification task. The task of the computer of some agent is to classify what do you see in each of these images. For example, this is a mite. Here the model outputs the probability that it thinks that this is a mite, the probability that it thinks that this is a black widow. This is the ImageNet classification. Until 2011, all our rational machines, these Turing machines and coding, which is the way of implementing rational kind of logic, all these machines didn't manage to achieve human performance. So they were very sophisticated logical machines, but they didn't manage to do the same as humans, to perform as good as humans. So indeed, the limits of deductive logic is oversimplification, what constitutes an object, as you say, and what do we do the deductive logic on? This is something that is not defined well. And humans are not doing it, they're doing something else and they are more efficient. So now we will try to take it to the other way. And this goes very, very early to School of Athens, perhaps the first kind of university, although it was very different. We were already in this university, Plato were more focused on this abstract ideas of abstract kind of deductive logic, of putting more focus on these heightened, and his follower Aristotle pointing down to look at the data, at the world itself, and indeed he constructed all the sciences or the natural sciences that we today studying. And of course, they work together in this university. With respect to Rene Descartes, the philosopher that followed him, John Locke, is kind of the founder of the Empiricism approach, which is gaining knowledge through observation and experience. So data knowledge, data-driven statistical learning. This is an approach to the extreme of it. He says that we are all a blank slate, and we are just learning things from experience when we were born. This is the other end of this argument. How does the brain do this empiricistic approach? How do we do the things that as we demonstrated, you can do? So in neuroscience, we know that, for example, the visual input goes through a cascade of layers of neurons. When in the first part of the brain, the neurons kind of represent simple things like lines, and as you go up in the layers, it represents more and more complicated objects, kind of such as cats and flowers, and this is how we identify these objects. We identify the things that we do deductive logic on. And importantly, the brain also changes the weight between different layers in order to classify new things. So the brain is a learning machine. Inspired by the brain, researchers have built deep artificial neural networks, where you also have a cascade of propagation of information, a flow of information from the input through layers, different layers, to the output layer. If you return to the first kind of slide with the matrix multiplication, so X is like the input to this network, and then it is multiplied by W to get the output of the first layer, and then it is multiplied again by another with another weight matrix and another one until you get to the output of the network. So here is and as I said, neural networks are trained. This is a demonstration from 3 blue, 1 brown. Now it is done. Of course, this is we will learn about it in detail, but you pass a certain input, you get some output. Usually with random weights, the output won't match what you want. So you're training the network by changing the weights between the layers until you reach you get a network that classifies the images correctly. Okay, so this is how the kind of brain is the way the brain does these things is modeled by today's deep learning tools. And after learning, you get an input layer, you get a network that kind of represents similar things like the brain. You get in the first part of the network things that represent patterns of small things, lines, and things like that. And in the higher places, you see representation of objects, or face features, etc. So for the rationalist, you want to simplify a complex system that has n variables, a large number of variables, to a simple one. For example, this is a simplification. It is a function of this complicated system, and the simplification can be, for example, a reduction. You take just one of the variables. So by deduction, you can do some deductive logic. or you look at the statistics. Stars, center of mass, neurons, animals, all those things are some simplifications of nature on which we do logic. The empiricist approach is to statistically learn this simplification. So this Y, this object that we try to represent, have some parameters to it called theta here. Those are the weights, and the output Y is it is called the latent variable. This is the objects that we think that are hidden in the input. This is why they call latent. They are hidden like behind the. Once you have this, you need to train the network by changing these parameters, these theta parameters, the weights, and the way that you change these weights is by learning. And logic in this empiricist approach is the learning rule. Okay, this is the logic that we need to write. We need to write the learning rule. This is kind of a top-down logic. You just say what are the requirements from the network, the logical requirements. For example, I asked you what is common between all of you. This was a rational kind of question, but and this is a kind of question, the kind of questions that we will implement in deep networks. We'll ask what is the common things between, what is common between different inputs and things like that. The bottom-up logical steps that I asked you and you didn't know how to answer, we are achieved by they are implicitly learned. They are achieved by the network by learning. So the way that inputs are transferred to these objects will be via many logical steps that we have not programmed by our own hands. They will be learned by this top-down logic. Indeed, these networks achieve human performance in ImageNet and even exceeded human performance. And I think that today I don't need to tell you how deep learning is successful in things. But I want to show you what it is used for in fields that are similar to our field. What can you use it for? So one kind of usage is for understanding the brain. You want to know how the brain works. We presumably say that deep learning is a model of the brain. So perhaps we can learn about the brain by learning deep learning. This is a recent paper that tried to do that. The question that is being answered is, what is the high-level visual cortex representing? So, as I told you before, the visual cortex first represents the things that are simple, and as we go deep in the visual pathway, you get representations that we think that represent objects, but this paper shows that these deep layers are not exactly representing objects. They argue that it represents something else. So what have they done? They use the neural network deep learning model that is called the CLIP. It is trained by, okay, I will go through the steps. You take an image, you pass it through through a kind of a neural network, an encoder it is called, and you get this Y, this latent variable output Y. You do the same thing with text. The text are attached in the training set. You have text that attached to images from the internet, for example. You have the description of the images. So they pass this simple short text, this prompt, to a text encoder. You also get the latent variable of the text, and this deep learning model is trained to match the latent variable of the image encoder and the latent variable of the text encoder. So the text encoder should output the same thing as the image encoder, given that there is a match between the image and the text. And this is what is used for DALI, by the way. This is the model that DALI used. You then write a prompt and you get a latent variable that is also corresponding to something that is image related, and then you have a generative model, which is not here, that outputs the correct image. Here they show that these latent variables are good predictors for the activity of high-level cortex neurons. What does it mean? They argue that this means that these high-level cortical neurons don't represent objects like cats and flowers, but they represent objects in context, because these latent variables are the learning objective was to match it with text. So it represents things like a book on a shelf, a book on a table. If this is what we see here, a book on a table. Things that are more in context. So we learned something new about the brain. Yeah, do you have any questions about it? It is a nice recent work. To make sure that they have compared it with a different network that was trained only on object recognition, just labels of cats, dogs, and things like that. And it explains these high-level brain areas better than the object recognition model. Therefore, it is perhaps more close to representing these objects in context. Okay, this is my work. I wanted to just briefly show what I do. I use deep learning to understand the cognition. Things like I asked you in the start of the class, what is common between things. Here we try to see how humans, to model the way humans find relations between different inputs, and specifically, if you can find a relation that explains how this how the sequence of inputs here, then you will be able to answer this intelligence test. And in my work, I try to see the ability of these deep learning models to solve this test without prior training. So when they are naive, this is my work. I use relation networks that tries to classify these latent variables, this joint of latent variables of the inputs. So this is perhaps we'll get to something that's similar to that or not. We'll see. By the way, do you know what the answer to this question? I cannot put 3 this side. Yeah, you're correct. The rule here is that it is a triangle, square, triangle, square, triangle. Okay. For neuroscientists in your lab, you can use it to just measure things and to do your research work. I think this is a motivation for many of you. A good library for doing that is called Deep LabCat. You can already use it. I'm not sure that even you need to learn deep learning to use it. It is a very developed open source library that enables you to mark, to identify locations in videos, in images, a certain the position of this field, for example. Or here you can track the pupil of the mouse and get the output of it to see how stressed it is, perhaps, and track mouse and mice and slides. So this is a very useful tool done by deep learning, and if you're interested, look at Deep LabCat. Okay, so let's try to bring everything together and combine the statistical learning with a rational approach. So today we have a very large statistical model, ChatGPT, that learns the statistics of language, and if the empiricists are correct, it learned so many things. It's seen so many things that it perhaps can actually do rational kind of inferences. So I tested it, and let's close the light. Yeah, I hope that you see it, that it's not too small. If it is too small, I will read it. It is too small. Yeah, I will read it to you. I asked from ChatGPT, which is also the TA of this course, to act as a Python interpreter. This is a good time to ask, how many of you know how to code in Python? So all of you, 100%? That's great. Okay. So, and you also work with PyCharm, things like that, you know, to debug things. Oh, so we can perhaps skip the start of the course. This is a good indication. Let me just see how many students are in the Zoom. So no one, I hope. Perhaps they are building on the recorded class, and then I don't know whether to teach Python or not. Okay, but I asked ChatGPT to be a Python interpreter. All this text, which I taken from somewhere else, is just trying to make sure that it won't write anything in addition to writing the output of the interpreter. My first command is print hello world, and it indeed works as it is a Python interpreter. You all know NumPy? Okay, great. So as you can see, it indeed works as a Python interpreter. Even managed to do this complicated, perhaps complicated thing of knowing that a list of A multiplied by 2 should return a list that is double in its length. Just multiply the list instead of multiplying with the values within the array. It was very impressive. I then tried to ask it to make it stuck like actual interpreters by doing some while through print high, and it didn't got stuck in the same problem that a Turing machine, that a machine that is doing only what you ask out of it, which works as rationally, wouldn't get stuck in. Statistically, it learned that this is a better answer to give to the user. So it made me think that perhaps this might be the way that we will program things in the future, that we can do all things of programming using statistical learning machines, perhaps even build operating systems. Those are my crazy thoughts, and this even got me more excited. I did an exit command, and then again print A, and the output is this A. So it is more smart. It is smarter than a simple machine in some sense. But yeah, this is really blowing my mind. But then there are problems, of course. Which is heavier, kilogram of feathers or 2 kilograms of bricks, and perhaps you've seen it, and it answers that both the kilogram of feathers and the 2 kilograms of bricks weigh the same amount, which is 1 kilogram. And of course, it has seen this question only in the context of this kind of logic thing. And statistical learning have its problems. Okay, so that was the kind of philosophical introduction to the course. And we will get to the practical side of it after the break. So the break is in 2 minutes. I think that this is a good time to start. So let's take a break.